Hi everyone, Tina here, and today I'd like to talk about hypothesis testing. Hypothesis testing is essentially using statistics to decide whether or not there's enough evidence to reject a hypothesis or a statement of something which is believed to be true. In this video, I want to focus on hypothesis testing involving the binomial distribution, which you'll come across during year 1 of your A-level course. I'll point out the different types of question you can be asked first, and then we'll go through an example of each one. So here are the 4 types of binomial hypothesis testing question you can be asked. Some will ask you to test a hypothesis given some sample data, and some will ask you to find a critical region. We call the test a one-tailed test if it involves probabilities or proportions with this or this inequality symbol, and two-tailed if the alternative hypothesis involves testing something to be not equal to something else. You'll see the difference between one-tailed and two-tailed when we go through the examples. Let's start with example 1, testing a hypothesis given sample data, and this is going to be a one-tailed test. Question says, the standard treatment for a particular disease has a 2/5 probability of success. A new drug has been produced which has been successful with 11 out of 20 patients tested. The leading doctor claims that the new drug represents an improvement on the standard treatment. Test the claim made by the doctor at a 5% significance level. First thing we want to do here is state our null and alternative hypotheses. We use the notation H0 or H0 for the null hypothesis and notation H1 for the alternative hypothesis. In this case, the null hypothesis is P equals 2/5, because that is the current probability of success for the current standard treatment. In this case, the alternative hypothesis that we want to test is P is greater than 2/5. This is because it says the leading doctor claims that the new drug represents an improvement on the standard treatment. The fact that the inequality is greater than means this is a one-tailed test, and this means the significance level is going to stay at 5%. Good idea to write this as a decimal at this point, so 0.05. Next, I like to write down the distribution that we're working with. So in this case, I would say something like, if H0 is true, then X is binomially distributed with parameters 20 and 2/5, because 20 is the number of patients being tested and 2/5 is the current probability of success. To do the test, we want to find the probability that X is greater than or equal to 11. Using greater than or equal to, because the alternative hypothesis is also using greater than. We're using 11 because that's how many successful patients we had in our sample. If you work this probability out using your calculator, you will get 0.1275. Now we need to decide whether that's significant or not. So to do this, I like to draw a number line from 0% to 100%. I then put my significance level on, so in this case 5%, and then I make a mark to say anything between 0 and 5% would be deemed as significant. I then think about where 0.1275 would lie on this line, maybe somewhere here, and it's greater than 0.05. As you can see from the number line, it doesn't lie in that significant area, so this is not significant. That means we can now make our conclusion and say something like insufficient evidence to reject H0. You should then always make a comment in relation to the context of the question. So in this case, something like, i.e., not enough evidence to support the doctor's claim that the new drug represents an improvement on the standard treatment. And that's the hypothesis test done. Example 2, this is going to involve sample data, but this time be a two-tailed test. It says it's been found that in restaurant 1, the ratio of non-vegetarian to vegetarian meals ordered is 2:1. In restaurant 2, in a random sample of 10 people ordering meals, 1 ordered a vegetarian meal. Using a 5% level of significance, test whether the proportion of people eating vegetarian meals in restaurant 2 is different to that in restaurant 1. For this question, before we write our null and alternative hypotheses, it's probably a good idea to outline what P is going to be. So in this case, we can say something like, let P be equal to proportion of people ordering a vegetarian meal. Then we can say H0 or H0 is P equals 1/3, because the ratio of non-vegetarian to vegetarian was 2:1. Then we've got H1, and in this case, because we just want to test whether the proportion is different, that means we're testing whether P is not equal to 1/3. The fact that we've got that not equals to symbol means it's a two-tailed test, and that means you want to divide your significance level by 2. So in this case, 0.05 divided by 2 would be 0.025. So two-tailed, dividing the significance level by 2. Next, I would write, if H0 is true, then X is binomially distributed, and this time 10 people, probability of success 1/3, where success in this case is ordering a vegetarian meal. Now, in order to decide which probability to work out, we should think about the expected value in a sample of 10 of people ordering vegetarian meals. So what is the expected value in a sample of 10, that would be a third of the people, so 3.3 recurring, or roughly 3 people. That's how many people we would expect to order a vegetarian meal if this ratio or proportion was a third. In the sample in restaurant 2, only 1 person ordered a vegetarian meal. So that means we want to test the lower tail. In other words, we want to find the probability that X is less than or equal to 1. Again, working this out in your calculator, you'll get 0.104. You can then draw a number line if you wish, 0%, 100%. In this case, what will be significant is if it's between 0 and 2.5%, because remember we divided the 5% by 2. So this place here is significant. 0.104 might be here somewhere, so it's greater than 0.025, meaning not significant. Once you've decided that, you can write your conclusion. So our conclusion here will be insufficient evidence to reject H0. Again, we need to make a comment in the context of the question. So we could say something like, i.e., not enough evidence to support the hypothesis that the proportion of people eating vegetarian meals in restaurant 2 is different to that in restaurant 1. So I just want to go back to that probability of testing whether X is less than or equal to 1. So we use 1 because that's what we observed in the sample. But the reason we did less than or equal to is because in a sample of 10, you would only expect around 3 people to order a vegetarian meal. But the fact that only 1 person ordered it in the sample means that's on the lower end of what's expected. So you want to test that probability and see how small it would be in this context. Example 3, find a critical region, and it's going to be a one-tailed test. So in this case, it says a single observation is taken from a discrete random variable x, which is binomially distributed with parameters 35 and 0.4, to test h0 p equals 0.4 against h1 p is less than 0.4. Part A, using a 5% level of significance, find the critical region for this test. Now, a critical region is the set of values for which you would reject h0. In other words, it's the observations that would lead you to enough evidence to reject the null hypothesis. Let's find that critical region. So we should always state what h0 and h1 are. In this case, they're given. So h0 is p equals 0.4 and h1 is p is less than 0.4. So it's a less than inequality, means it's one-tailed. So the significance level can stay at 0.05. In this case, if h0 is true, then x is binomially distributed 35, 0.4. And here's where we need to do something different. So we need to be able to see the probabilities for a bunch of different observation values. One of the ways you can do this is by using the binomial CD list function in your calculator. This allows you to get a table of values for different x values, and then it will give you the probability that x is less than or equal to x in each of those cases. So if we do that in our calculator and then scan down the list, I'll point out 2 interesting observations. So one is when x is 8, the probability in this case is 0.0259. And then the next one down, when x is 9, the probability is 0.0575. And then it goes on. So these 2 are interesting because this is where the probability flicks from being below and above the significance level of 0.05. So when x is 8, the probability is 0.0259. This is less than 0.05, so this is the one we're interested in. You're looking for the last probability down the list that is less than 0.05. But do be careful because some questions will ask for probabilities to be as close as possible to 0.05 instead. But in this case, we're going to go for the one that is less than 0.05. This means we can now write our answer down. So the critical region is going to be x is less than or equal to 8. Because any x values less than or equal to 8 will have a probability less than 0.05. For part B, state the critical value for this test. That's going to be 8 because that's the value on the boundary of your inequality. The actual significance level for part C, that is just the probability that you found for when x is 8. As a percentage, that's 2.59%, and generally the actual significance level will always be less than the significance level of the test. So less than 5% in this case looks good. Lastly, for part D, we're told that the actual value for the observation was 6. State the conclusion that would be reached for this test. Now, because 6 is less than 8, that means it's inside the critical region. That means we have sufficient evidence to reject H0 in this case and support H1 that P is in fact less than 0.4. If the value of the observation was outside the critical region, then we wouldn't have sufficient evidence to reject the null hypothesis. Last example, and it's going to be a critical region two-tailed question. It says, it is reported that nationally in the UK, 4 out of 5 people are right-handed. A researcher believes that the proportion of right-handed children in the UK differs from the national proportion for all people. To test his belief, he takes a random sample of 30 children and records the number of children who write with their right hand. Part A. Using a 10% level of significance, find the critical region for this hypothesis test. So again, for this one, I'm going to define what P is first. So I'm going to say let P be equal to proportion of right-handed people. H0, P is equal to 4/5, just like the national proportion. And then H1, P is different to or not equal to 4/5. Again, not equal to because we're just told that the researcher believes that the right-handed children proportion differs from the national proportion. And because it's two-tailed, it means we need to divide our significance level by 2 again. So 0.1 divided by 2, 0.05. Next, I would write if H0 is true, then X is binomially distributed with parameters 30 and 4/5. And then I would use the binomial CD list function again. So you'll get a table of X values and the corresponding probabilities. For the lower tail, it's similar to the previous example. So you want to look for where the probabilities flip from being less than 0.05 to being over 0.05. And in this case, it's when X is 19, the probability is 0.0256. And when X is 20, the probability goes up to 0.061. So again, we're looking for probabilities less than 0.05. And in this case, it's this one when X is 19. So at this point, I'd probably make a note on the side to remind myself that this means the probability that X is less than or equal to 19 equals 0.0256, which is less than 0.05. For the upper tail or higher observations, you want to look for something slightly different. So if we go further down, the interesting ones are 26 and 27, corresponding probabilities 0.8772 and 0.9558. Now, the reason I say these are interesting is because here you want to look for a probability greater than 1 minus 0.05, which is 0.95. Because of the way binomial probabilities work, if you want the probability that X is greater than or equal to something, you have to do 1 minus the probability that it's less than or equal to something else. So in this case, 27 had a probability of 0.9558, which means the probability that X is greater than or equal to 28 would be 1 minus the probability that X is less than or equal to 27, which in this case is 1 minus 0.9558, which is 0.0442, which is in turn less than 0.05. That upper tail is always more confusing, but if you look for probabilities greater than 1 minus the significance level, that can really help. So now we have our critical region, because we can say based on this that the critical region is X is less than or equal to 19, or X is greater than or equal to 28. Just a reminder, the critical region is the set of values for X for which you would reject the null hypothesis. So you want to state those X values clearly. Part B, state the actual significance level. For a two-tailed test, this will be the two probabilities added together. So first it was 0.0256, and then we had 0.0442. Let's add those together. That gives 0.0696, 6.96%. Again, less than 10%, so that looks good. And then lastly, part C says out of the 30 children in the sample, 22 were recorded as writing with their right hand. Comment on the researcher's belief based on this observation. Okay, so 22 is greater than 19 and it's less than 28. Either way, it's not inside the critical region. That means in this case, we have insufficient evidence to reject H0, i.e. not enough evidence to support the researcher's belief that the proportion of right-handed children in the UK differs from the national proportion. That's it for now. If you found this video useful, please do remember to like, comment and subscribe to my channel if you haven't already, and do share this with anyone else that you think might find it helpful. Thanks, and see you next time.